Hello and welcome back. So we've been looking at turning points and the uses, and by turning points I mean in calculus. So we've been using turning points to solve problems in engineering and in science. And we've come to the stage now where we're going to have a look at a tray. So we're going to make a tray. So think about this scenario. So you're working in maybe in an office, maybe you're working in a factory you may be an engineer, and you need to make a tray to catch drips. So maybe it's underneath a machine, it's going to be an oil tray. Maybe it's under the printer in the office that's leaking ink for some reason. Maybe it's under the coffee machine, so you're getting sticky coffee all over the floor, so you need to make a tray to catch it. So because you're the engineer, you're given the job of getting this tray made up. So you go down to the sheet metal department. So you're working in a place that's got a sheet metal shop, very handy. So you go down there and you dig around in the back of the guillotine and you pull out this piece of plate, and this piece of plate happens to be 360 millimeters by 240 millimeters. So you think to yourself, aha, if I have these corners cut out, this folded up, corners welded up, I've got myself a tray. So you go to the sheet metal worker. Now this sheet metal worker, bear in mind, is the world's greatest sheet metal worker ever. It can weld anything. He can make anything out of sheet metal work, but he's not a maths genius. So you say to him, I want you to cut these corners out and fold this up for me please, and make me a tray that I can catch my drips in, but I want it to be the optimum volume, so the maximum part of volume. So he looks at you and he goes, let me explain. If I cut these corners out too big, then I'll end up with a tall, thin box, but it won't hold as much. If I don't cut them big enough, I'll end up with almost a flat box tray that won't hold so much. So he looks at you and he goes, So you go, hold on, I'll be back in 10 minutes, just leave it with me. So off you go to the office, you get your piece of paper out and you start working out the maths. And that's what we're going to do here. So if I just have a look at the next slide. Okay, so what I meant by this scenario, if you think about it, you can cut the corners out like this. So we've got X here, and this X is the same this way, this way, this way, this way, and this way. So X is the same for every corner. So if I do that, then I can get, if I cut a small amount out, I can get a tray that's very shallow, like this one. In fact, if you think about it, this height here could even be as low as 0.5 of a millimeter, 0.1 of a millimeter, though that would take some folding, but obviously wouldn't hold. In fact, if you made the X 0, then it wouldn't hold anything, would it? It'd just be a flat piece of plate, so your coffee from your coffee machine would go all over the place. Now the other extreme is to cut out big corners, and then you'd get a long thin box like this. This is not really correctly to proportion, but you get the gist of the idea. So you get this long, tall, thin box, and this distance here would be your X, would be the result of cutting X out of your tray. So you've got a thin bit left. This again could be such a small gap, again 0.5 a millimeter, 0.1 of a millimeter. So that would be one extreme. This would be the other extreme. And if I was to plot it, so why is my pen not working? It helps if you turn it on. Right. So if I plotted this, I would get something like I suppose like a bell shape. Okay, like this, where X is 0, I would get 0 volume, and where X reaches a maximum point, I will get 0, because that's when that gap there would be 0. So it'd be just two flat bits of plate really, so it'd be useless. And in the middle we've got an optimization point, an optimized point. So that's when our X is at its best. We'll call it X0 for the argument's sake. So that's its optimized point there, where we'll get the maximum amount of volume. So how do we do it? It's obviously we've already covered turning points, so I'm going to go through this fairly quickly. So if I go too fast, obviously you can go through it again and check, but really you need to be looking at maybe my first video on this presentation on turning points if you're not following this. Okay, so let's have a look. So if I get a fresh slide up, so the volume of a box is V equals, so it's going to be the width times the length times the height. So that's fairly standard stuff. Okay, so let's come up with a formula for that. What I'll do is I'll write out the formula, then I'll explain it. So we've got the width, the volume is equal to the width, which is 360 minus 2x. I'll explain that in a second. Times the length, which is 240 minus 2x, and all that's times the height, which is just x. So what does that mean? Let's go back a bit. So if you look at this, we've got, there's a 360 from there to there. So to make the volume of the box, it's going to be this distance here. It's basically the bottom of the tray. So from there to there, so how's that measurement found? Well, it's 360 minus this x, so it's 2x. And same goes for this, the width of it, or the length of it, shall we say, is 240 minus this x and this x. So that's where the formulas come from. Okay, then times x is the height. Obviously x has to be the same measurements, or your height wouldn't be equal. You'd have one height that was taller than another, which would be pointless and wouldn't work in an exercise anyway. Okay, so if I'm going to multiply that out, or I'm going to show you multiply it out. I'm not going to go through this. This is just basic maths. You may want to work on this for yourself, have a go for the practice, but you'll just have to take my word for this. We end up with, so I'm multiplying out the brackets, I end up with 86400x minus 480 x squared minus 720 x squared plus 4x to the 3. Okay. Now if I simplify that, so add my like terms together, rearrange it into the order of the highest power first, and we'll get this. V equals, so 4x3 minus 1200 x squared plus 86400x. Okay, so we've got a formula for the volume. So we're looking for the optimum x value. So what's the next step? So we need to, at this stage, we need to differentiate. So it's dv dx. So we're differentiating in relation to x for the volume to find an optimum x. So if I differentiate that, I will get, so 3 into the 4 gives me 12x to the power 2, take 1 from the power, minus 2400x to the 1, plus 86400, and the x is disappeared, so the 1 from the x goes to the front and we take 1 from it. Anyway, we end up with 86400. I hope you can remember that. Okay, so that's your standard differentiation. Okay, what have we got here? We've got a quadratic equation. We've got x to the 2, x to the 1 and an x to a 0 basically. So it's a quadratic. So we can solve this by doing factorization, but we're not going to do that. We're going to do it by, we're going to use the formula. Now if you remember, the formula is this. We're going to cheat here because you don't get prizes for doing things the hard way, not when there's an easy way. What's the point of technology? Okay, so if you remember this formula, and I've got to be honest, I don't always remember it, I often have to look it up. It's your quadratic formula. Okay, so I can do the maths of this. Okay, so this 12 here would be at A term, this 2,400 would be a B term, and this 8,600 would be a C term. And yes, I do recognise and admit it that you can actually cancel this down to simpler numbers. So you could cancel this down by multiplying through by 12, I believe. Dividing through by 12 rather. So you would actually simplify this maths, but I'm not going to bother, and the reason I'm not going to bother is because I'm not actually going to do the maths. I'm going to reach for my phone and I'm going to put it into my phone. I have an app on my phone. Let me just shuffle the screen up a little bit. And there's things online and there's many tools, so you can get an app for your phone. There's many of them, and I'm not going to promote any particular make or brand or version or even other type of phone. So from my app on my phone, I've got these two values. I've got x equals 152.915, whoops, or 47.085. Okay, so as with normal with the quadratic formula, you get two answers, and the question is which one's the correct one. Sometimes it's both, depends on the situation. In this case, only one can be correct. So 152 or 47. Okay, right, let's have a look at this logically. If I go back up to our original, so we've got 240 millimeters here. So if I cut out from 240 millimeters 152.9, 253 millimeters times 2, it would actually cut everything away. So I'd actually end up with a thin bit left here. It wouldn't be a tray at all, it'd be silly. So it's obviously not that one. Now 47 millimeters does make sense. So it's going to be 47 millimeters. Let's just scroll up a little bit. So in that case, it must be this one that's correct. Okay. Now, as always, we need to check that this actually gives us that it's this shape and gives us a maximum. Okay, so x, which is 47 there. Let's use my pen here. 47.1 really, I suppose, if we round it up, 0.1. It's that shape and not the other way, this a minimum. Okay, logic tells us it's a maximum, but we need to do a test. And if you remember, I said the ways to do it were to move two ways. Slightly longer but more precise method is to move slightly to the left. So if, by the way, at some point I need to point out here, what we're looking for is when the gradient is 0, which is this point here. I know I've covered this in the previous slides, but let me just restate it. So we're looking for all this to be equal to 0. So that's when the gradient is 0, because remember, this is what this tells you what the gradient is. So this is why we use this formula to find the two values. So these are the two values when the gradient is 0. And as we've said, this one is silly. This is in some non-real world, shall we say. Anyway, okay, so going back to my thing, if I move slightly to the left, so say 47, we'll do it, put 47 into my values of x, I would get the gradients at that point at 47. And if I got a negative gradient like that for this, and then if I move to the right, let's say 47.5, and I get positive gradients, we know it's that shape, a U shape. Obviously if I get the other shape, which we're not expecting, but if I did, it would mean that this was what we call a maxima, and we're looking for the minima, this shape, a U shape, rather than a mountain. Okay, so that's this one way of doing it. That's the most precise way. Another way, if you remember, is to do the double differentiation. So we differentiate what we've got here again, and I'm going to shuffle up a bit more here. Okay, so we do a double differentiation, supposed to be a d, dx squared equals, so it's this term here differentiated again, so we would get 24x um, 24x minus 2400, and the rest is a constant, so it disappears. So if we look at that, so if x is 47, so 24, if we say make x 50, round it up to 50, 24 times x would give us 1200 minus 24,000. If you remember what I said previously on the previous slides, is we don't care what the answer is, we only care about the sign. Is it a positive or a negative? And if you remember, I said that if both were negatives, you get a negative answer. If both were positives, you get a positive answer, which will make it easy. You don't even need to think about the numbers. But because we've got a positive and a negative, we need to do a bit of the maths just to see if we get a positive answer or a negative answer. Obviously, the biggest number wins. In this case, the 2,400 subtracted from 1,200 gives us a negative. And if you remember, hopefully you do, a negative is equal to a maximum value. Okay, now taking our test that a little bit further, we know this is the wrong answer, but if we put that in 153 times x, I'm going to reach for my calculator here, 152 times 24 equals 3,648. Take 2,400 from that and we get a positive number, because the positive term is the biggest, so that would be a minima. So obviously that doesn't work, so it just verifies what we've already worked out from common sense. Okay, so we've proved it. So there's only one thing left to do in this exercise, and that is what actually is the volume. And I'm not going to do that, I'm going to leave you to do that. It's just a case of putting your numbers, this 47, into your original formula and working out what the volume of the box is. And this is the kind of thing you would need to do if you're doing this just don't leave it at this stage. If you're doing it in an exam, my students are doing BTEC, so they get the merits and distinctions from adding additional information. So this is definitely the information you have to cover. So what you would have to be, what you're going to be doing is, when a tutor, the teacher, marks your work, he's looking for marks, and he's looking for understanding. So the more information you can put in there to show that you understand what's going on, that you understand the whole process, that you've got a deep understanding of it, the more likely you are to get those better marks. Whether you're doing a BTEC where you're looking for the merit and distinction, or whether you're doing an exam. If you're doing an exam, the examiner's looking for the maximum mark. If they're a good marker, they're looking for the additional marks they can give you for understanding. So the more information you can get in there, the better. So obviously do your test, explain about the 152.915, give some understanding of that, do your little graph here for sure, and this little mark, this with a 47.1 for example, show that you know what's going on, explain that this negative gives you a maximum value, and then work out your volume. So all these are things you must cover if you want those extra marks. Okay, thank you for listening.